It's a pleasure to introduce Michael Harrison from Lee University, or now Carnegie Mellon. What? Carnegie Mellon. Pittsburgh?
Pittsburgh, yes.
He will speak about totally non-parallel immersions.
Thank you. Well, thank you very much for the invitation, and also to Marcos and Jamile for their generosity hosting me for my visit. Okay, so I will start off. In this talk, M will always be a smooth n-dimensional manifold. And let me just recall definition of immersion. And I will assume pretty much all maps go into Euclidean space. So I have a map is an immersion. If for all x, my differential has rank n, I will always assume q is greater than or equal to n. And equivalently, we could say this differential is a bundle monomorphism. Just means injective on each fiber. And now I will define totally non-parallel. So for an immersion, I can always look at the tangent space in the image in Euclidean space. And I want to say that if you take any 2 points and you look at the tangent spaces, then there's no parallel lines in these 2 tangent spaces. So for every pair of distinct points, you look at your 2 tangent spaces, and you ask that they contain no parallel lines. We could also phrase this as saying that for every pair x and y, we can look at the dimension of the span of those 2 spaces, linear span. And that should be 2n, n dimensions for each space, no parallel lines. Okay, so how about some examples? If we just consider a one-dimensional space, then this would say that the curve has no parallel tangent lines. So the simplest example would be a parabola.
Sorry, the tangent spaces, the span of the tangent spaces of M, of f of M, or n, or RQ.
In the image, yes. In
The TF,
TF
Okay, U.N. FM here. Yes, yeah. Yes, thanks. Yes, so any 2 points, we look at the tangent lines and they're not parallel. And we could do something similar by associating these with complex space and considering this map, which in real coordinates, this. But this does not work if you consider quaternionic multiplication. If you try to do this for R4 to R8 with quaternion, that will not be totally non-parallel. How about a circle? Well, this cannot work because the image of a circle in R2 will always have actually many pairs of parallel lines. Example these. However, we can put S1 in R3. So this is no. This is a bit difficult to draw, but this is, I've drawn its shadow projected down to a plane, and then well, you should go around in such a way that you never go twice in the same direction. So it kind of loops around like this, yes. Well, in fact, there's a totally non-parallel immersion in every knot class. You can find one just by appropriately wrapping around the torus. No. Okay, so the main question is, if we start with a manifold M, what is the smallest dimension such that there exists this totally non-parallel immersion into this dimension. So for R, it's R2. For R, it's 2. For R2, it's 4. For S1, it's 3. And until recently, those were the only examples we knew where we had the sharp bound for this number. So let me talk about how to get some basic bounds on this number. So first of all, the target dimension better be this large, because you need every pair of tangent spaces to span this many dimensions. But if M is compact, we can get one more dimension, and the argument is similar to what I drew here for the circle. It's a Morse theory argument. If you look at a generic height function so we have our immersion. We look at, say, this height function. Generic height function will have at least two critical points. At those points, the tangent spaces will span two n dimensions, and this will be orthogonal to both tangent spaces. So you have one extra dimension there. So here's n and n1. So maybe I'll say look at critical points of a generic height function. And a basic existence result is a generic map if you have 4 n dimensions, then a generic map is totally non-parallel. Well, very roughly, maybe you could think of if M is n-dimensional, this is a condition on pairs of tangent spaces. Each tangent space has n dimensions, and each of these tangent spaces can range over an n-dimensional space. So we have n for each tangent space, and each one has a kind of n-dimensional parameter space. But if you want to formalize this, you should use some transversality theorem, multi-jet transversality. Okay, so we have a very rough bound for compact M. At least this. Okay, how about some stronger bounds? So if our manifold is just Euclidean space, then we can get stronger bounds by looking at symmetric bilinear maps, which have a property called non-singularity. So a symmetric bilinear map is called non-singular if it has this property. The only way to get 0 is if one of your factors is 0. And if B is symmetric, bilinear, non-singular, then we can look at the quadratic portion of this symmetric bilinear map and look at its graph, and this is totally non-parallel. So this is where these quadratic examples come from, where we have these, both come from these symmetric bilinear non-singular maps. The problem with quaternions is the multiplication is not symmetric, and that's really essential here. And let me give another example of a non-singular symmetric bilinear map. To say it simply, this is polynomial multiplication. I treat each of these as the coefficients of a polynomial and multiply them together. So if I write this out, n minus 1. I will end up pairing terms whose indices sum to the same thing. So the next will be this. Right, so this corresponds to polynomial multiplication. It's clear to see it's symmetric and bilinear. It's non-singular. The only way to get the zero polynomial is one of the factors is 0. So as a corollary, there exists totally non-parallel map from Rn into this plus n, R3n minus 1. It would be the graph of the quadratic portion of this map.
But sorry,
yeah.
What if we take Q just n plus 1 and non-singular? You get a smaller Q.
Sorry, I don't understand.
If you take just Q n plus 1,
Mm-hmm.
and so you need a non-singular symmetric to R.
Yes.
And that Q, you can do that.
No, that won't exist. Let's see.
No singular, it seems that it's not easy to find it's not singular.
Ah, it's much stronger than
The non-degenerate.
Okay.
Yes.
Zero implies one of okay. Sorry.
Yes.
Much stronger.
Well, another way to say it is if you fix x, then this should be full rank as a linear map.
Yes.
So for every x, this should be a full rank map. Yes, these are hard to find. Actually, these were studied a lot because these same maps induce embeddings of real projective space, which were a hot topic, and these were studied a lot by Ki-Yun Lam. He studied the space of these. And it's unknown for many dimensions what the smallest dimension here such that there exists a map is. Okay, and so this is regarding existence of totally non-parallel maps. And for more obstructions, let's observe let me define first. The configuration space of M, technically the ordered configuration space of pairs of points of M, is the product minus the diagonal. This is pairs of points which are not equal. And there's also the unordered configuration space. Which is just this modded out by this Z2 action, which switches our points. This is a free action because we deleted the points where they're equal. So this is a manifold. Okay, and if there exists totally non-parallel immersion, then this unordered configuration space immerses in this RQ. The proof is almost by definition. We'll define this map G well, it will be Z2 equivariant, but I'll just write it first. Just take the sum of these two. And we should check that it's an immersion. And just note that this differential at a point kind of splits into these differentials at x and y. But totally non-parallel means there's no parallel lines here. So these are all, this is all full rank. This is rank 2n. And it's Z2 equivariant, so it reduces to this unordered configuration space. So this allows us to compute some obstructions. We just have to look for obstructions to immersing unordered configuration spaces. And you can do this with Stiefel-Whitney classes. So if you take a manifold, you could actually maybe compute some obstructions, although it's difficult to do so. A related result for Rn totally non-parallel immersions induce immersions of projective space. And these immersions were very classically studied. So this is an alternate way to kind of compute obstructions. Okay, so although we can compute obstructions this way by computing obstructions to immersing these, this is very difficult. But recently, this was done by Don Davis, who was also kind of famous for studying these immersions of projective spaces, showed that if n is a power of 2, then this unordered configuration space of RPN does not immerse in R4n minus 2. So this yields a very strong bound because this one is generic, and now this is by this very strong bound in this case. And I was then able to show that it's exactly this. And the method is a kind of Whitney trick. So Whitney first showed that a generic map into 2n plus 1, R2n plus 1, is an embedding. And then studied the local embedding problem, which is immersion problem, and showed that a generic map into R2n is an immersion. So now you take an immersion, and it might not be globally an embedding, but he does this Whitney trick, which allows to show that there exists an embedding of any manifold into R2n. So maybe I'll briefly write that. So generic map in these dimensions is an embedding, but you can study the local embeddings or immersions and gain one more dimension. And then you kind of take an immersion and do this Whitney trick, and you can obtain at least there exists an embedding in these dimensions. Whitney trick. So this comes about by studying the local problem and then doing something global to resolve these global singularities and showing there exists an embedding globally. So here, I'm able to show that for any manifold, you can reduce this from 4n to 4n minus 1. Okay, so I want to switch gears a bit. So the proof of this is very, very technical, 20 or so pages, so I won't tell you all of that. But I want to explain the technique that I use. It's a H-principle technique, which I'll explain a little bit, called removal of singularities. And I want to explain it not for totally non-parallel immersions, but just for ordinary immersions. So let's go back to immersions. And by definition, an immersion induces this bundle monomorphism and we can phrase this by saying that the space of immersions, an element here is an immersion from M to RQ, there's an inclusion map into the space of monomorphisms. Given an immersion, just take its differential. But I want to point out, although differentials are examples of these, this space is purely algebraic. Forget about differentials. This is a vector bundle. This is a vector bundle. And you're looking at bundle maps between two vector bundles and asking that it's full rank on every fiber. So this space is has nothing to do necessarily with differentials of maps. The Smale-Hirsch theorem says that this inclusion map is a weak homotopy equivalence. Which just means that it induces an isomorphism on all of the homotopy groups. So although this has something to do with differential topology, and this is a purely algebraic set, they are kind of equivalent in this sense. They have the same homotopy groups. If we look just at pi 0, the fact that this is surjective on pi 0 would say if there exists a monomorphism of these two vector bundles, then there exists an immersion. So in some sense, it reduces this differential problem of looking for immersions between spaces to something purely algebraic. You can study monomorphisms using obstruction theory, for example. Injective would say if there exists two monomorphisms which are differentials, which are homotopic through monomorphisms, they are homotopic through immersions. A good example to keep in mind is this Whitney's classification of plane curves. Two plane curves in the plane. Two plane curves are homotopic if and only if they have the same winding number or tangential degree. This is just a special case of this when m is S1 and q is 2. So I use this term H principle. It's homotopy principle. And it's not an exact result, it's a type of result which relates some kind of differential data with some kind of algebraic data and says that they're equivalent under certain conditions. So this Smale-Hirsch was one of the first famous examples of an H principle statement. It was then studied a lot by Gromov and many others. And what I'd like to do is give a proof of a simple case of the Smale-Hirsch theorem. So I will prove I will take M closed, the target dimension strictly greater than the domain, and I will just show if there exists a monomorphism, then there exists an immersion. And this proof will use a technique called removal of singularities. Which was due to Gromov and Elie Ashberg. And the strategy is exactly the same as the one I used for totally non-parallel immersions. So if I have time, I'll explain how I can adapt that. Okay, so I will start with a monomorphism and I want to observe this is the same. I will consider this a monomorphism just like this. To explain, all of the interesting data of this bundle map is in the fibers. So I'm just going to forget about the map it covers from M to RQ. I may as well assume it's a constant map because the map it covers doesn't matter at all. This is the only interesting data is in the fiber. Is that okay? And this I will consider as a collection of Q1 forms. So I'm thinking of this map as Q different maps from Q linear maps from Tm to R, just in these coordinates on RQ. And in this language, monomorphism means this omega spans the cotangent bundle. Well, the omega, let me put omega I, span the cotangent bundle. Now, if, big if these are all exact, then we're done. Because if they're all exact, then there's a map F from M to RQ. This is the differential. They span the cotangent bundle. That's the definition of immersion. So if this is true for all I, then F is an immersion. And we're done. So the strategy is to inductively replace each of these while keeping monomorphism. If we can do this successfully for all Q of these, then we will be in exactly this situation and we'll have an immersion. Okay, so let's start with omega 1. And I want to replace omega 1 with dF1 while keeping the condition that they still span the cotangent bundle. And let's do something very stupid and just pick an arbitrary function f1 and see what happens. So idea, use for arbitrary function f1. Okay, but what could go wrong? So there's a certain space, which I'll call sigma 1, we'll look at this space this less than these at x. This is where we need to be careful. So notice there's no omega 1 here. We need to be careful here because on the complement, these already have full rank. On the complement of this set, the rank is n. It says and it really doesn't matter what df1 is. Because if the rank here is already n, then I really could add something to it and the rank will still be n. So on the complement of this set, I can do whatever I want.
So sigma is closed.
Yes. Yes, in fact, I put less than n here, but we started with something with rank n, and we just eliminated one of them, omega 1. So this is really here, the rank is exactly n minus 1. I started with n, I eliminated one vector, covector. Rank can drop by 1 at most. But anyway, yeah, the full rank set is open, so its complement is closed. Okay, so rank is n minus 1, so there exists one-dimensional kernel at each point here. And I will study this assumption for all x in this space. The kernel is not tangent to the space. So I have this picture. M is not Euclidean, but I'm drawing it as some three-dimensional. And here's my sigma 1. And at every point, the rank drops by 1. So there's a one-dimensional kernel, and I'm assuming it's transverse. So I have something like this picture. And note this I call K. K is actually a trivial line bundle. Because I started with something full rank. Here's the kernel of all of these. That must mean that omega 1 is non-zero on K. And now I claim I can make a replacement I'll take a non-zero section of this line bundle. Such that at every point, this has value 1. I'll define my function as 0 on this space, and then extend in the direction of my line bundle such that this matches this value, is just 1. So this is a trivial line bundle. I define as 0 on here, and then I can just extend however I like. And then I can extend arbitrarily to all of M, because it doesn't matter what the value of F1 is on the complement here. Okay, but this was a big assumption. So what happens if this does not hold? If it is not transverse, then at some points it's tangent, and we will define this subspace of points where it is tangent. So now our picture some points it's transverse, but then we have some subspace where this kernel is tangent to this space. But I will assume at least it's not tangent to this one. I will assume it's not tangent to this one. It's just tangent to this one. But I can do exactly the same strategy. I'll start here. I'll define my function as 0. By transversality with this assumption, I can extend into some neighborhood like this. And then I will extend to all of sigma 1. And then I will extend transversely and extend to all of m. Okay, so we can keep going with these assumptions. And we need to apply, well, let me remark, we could define sigma 1, 1, 1. And it's a theorem called the Thom-Boardman theorem. That for generic omega, these singularity spaces are all defined in terms of my omega. For generic omega, this sigma 1 is stratified by these subspaces. So in particular, there will be one of smallest dimension. We start there, we define our function as 0, extend, and continue until we've defined on this whole space. So the, yeah.
About 5 minutes.
5 minutes, okay. So the full argument would be we start with our monomorphism. We perturb it so that this is satisfied. And we're allowed to perturb it because this condition is an open condition. So we can perturb omega and replace, using this strategy, with this. And now we have this. We can perturb this as a function from m to r, and the rest of these as forms, to still get this genericity property, and use this to replace. So perturb and replace this. Okay, so you can continue this until they're all replaced and you end up with an immersion. So maybe I'll just make a few comments about trying to extend this to totally non-parallel immersions. So in this case, we have totally non-parallel immersion induces an immersion of this space. And I want to reverse this. I want to say if I start with an immersion of this space, can I get back to a totally non-parallel immersion using a similar replacement technique? So I'll think of G as Q functions to R. And I want to replace I want to replace in each spot this function with something like this, because if this is still an immersion, then F is totally non-parallel. The problem is that this condition, so if you think of G as a function here, such that its restriction here is an immersion, this is not open anymore, because by perturbing, you could mess up something near the diagonal of m cross m. Yes, so if I consider it as a map here, which is Z2 equivariant, then on the diagonal, this thing does not have rank 2n. So this condition on this open set is not open, and a perturbation could mess up near the diagonal. So we have a similar situation where we get some generic property, but we can't just perturb our G because we'll ruin the fact that it's an immersion. So it takes a lot of care near the diagonal to actually make this argument work. Okay, so I'll stop there.
Are there any questions or comments?
Are there some bounds if you are in the class of Riemannian manifolds and isometric inversions for non-parallel, totally non-parallel immersions?
We
So you require
isometric immersions.
So you also require the isometric immersion. I don't know.
But is that studied?
No. Well, no one studied this before me, so I can confidently say no, it has not been studied.
Well, thank
But,
you.
I mean, for instance, the immersion you get for the projective space
Mhm.
of 4n minus 1,
Mhm.
is it possible that that is isometric immersion with the canonical metric on the projective space, or no way?
I have no idea because just like this, it's not constructive at all. It's just always there exists some replacement where you could do this. It's,
Probably not, but I think the Veronese embedding is the smallest codimension probably for isometric inversion for the project. It's not true.
I don't know. What are the general dimensions for isometric immersions? Is it linear in n or like n squared or something? I don't know. I thought isometric immersions were much higher dimension in general than this, but maybe I'm wrong.
Well, thank you very much.
Thank you.